Hello everyone, welcome to the next video of our AELD lab. So in the previous video, we discussed how to create the block diagram for our FFT accelerator. So in this video, we will start with our application development. So we'll create the application project. So file, application project. So here we'll write FFT demo. Then I'll start with the hello world. So in the Hello World project, what we will do, we'll start with our previous 8-bit 8.50 program, and then we'll modify that 8.50 program to work on to include the hardware acceleration part. So what I'm going to do, I'm going to I'm going to replace the Hello World original file with the FFT 8.50 code, which we did in our previous lab. So it will take some time to build. Okay, after the build is finished, now we need to first check whether the code is working fine or not. So what I'll do is that I'll just check it on my local PC, whether the code is working fine or not. Okay. Okay, so I'll just open the Terraterm. I don't need a FPGA to run this code because this is the purely on the processor. So I'll just use the processor. Again, I'm doing it on my local board. For the remote board, the process will be different. So I'll go to the project, run as, launch on hardware. So the the code is being downloaded on the hardware, and we will see if it is working or not. Okay, so I make sure that you have selected the local board in case you are using the local board. So in the previous case, I didn't select the local board. So run configuration in the local board. I'm not going to use the FPGA, so I have deselected the program FPGA1, and then I'll do the run. It will ask whether the FPGA is not configured. You want to continue? Yes. I don't need a FPGA for this one. So you can see that the code is working fine on the processor part. Now we need to modify this code to incorporate the hardware one. So the first thing we need to do is that we need to incorporate the DMA, and then we need to configure the DMA. So in order to use the DMA, we need to find out the corresponding DMA header file. So we'll go to the BSP and we'll go to the library source, and if you see in the AXI DMA, you will find the corresponding DMA header file xaxidma.h. You will see one more DMA, which is the DMA PS. This is the DMA present in the processing system. You will know more about this in our theory part. So here we are going to use the DMA xdma.h. So we need to include that file in our project. So I have included axidma.h file in our project. Okay. So this is the header file for DMA. So this is the first step we need to do. Okay. Then you need to know that you need to understand that all the hardware file like xDMA details, the DMA details, what is its base address, what are the register address, all the things will be there in the xparameter.h file as discussed before. So we need to make sure that we include that xparameter.h file in our slide. Okay. So this xparameter contains all the information about the hardware blocks. Okay, so if you go to the xparameter.h file, you will see that you can see this is our DMA, and all the information is present in about the DMA is present here. Similarly, for other IP in the future, we'll use more IP. So all the information will be present here in the xparameter.h. So you can see the peripherals details are also there. Our UART details are also there in this file. So this is a very important file. Okay, so now we have defined the xparameter.h file. That is done. Now second step is that we will go to our main code. Now in our main code, you can see that we have defined the input, which will be the same for our software as well as hardware. Now this is the output of the software. So what we'll do, the FFT output of the PS, we'll use the PS for the software, and then we'll define the another variable which will be the FFT output for the hardware. Okay, so this is for the PL. Make sure you make the changes everywhere. This is for the PL. Okay, so what we'll do to minimize the changes, we don't change it here. We'll make it as a FFT. Only for new output, we'll make it as a PL output. Okay, so the FFT here it is a PS output, and this is FFT. This is the PL output. So this is done. Similarly, for the time start and the stop, we'll need it for the PS as well as the PL. So we need to define it for the PS as well as the PL. So this is the next step. We need to take care that we define it for the PS and PL. Okay, so this is done. Then we print the output. We perform the FFT on this one, and then FFT output FFT. We can say that this is the PS output. Okay, so this is the one we will define it here, PS output. Okay, then let's keep this part for later, because we will do this display after we complete the hardware as well as software. Now come to the hardware part. Now hardware part, we need to perform the FFT on hardware. That means we need to send the data to the DMA, and we need to receive the data from the DMA. For that, we need to configure the DMA. For that, we need to incorporate all the information about the DMA. Now this is the few set of steps we need to perform for every hardware IP we use. For example, if you go to the xdma.h file, you will see that all the information how to use the IP is there in this one. Okay, over the time we will get to know more about this detail, but you will see that in every IP there will be two structure. One structure is for the DMA, which you are going to DMA instance, which you are going to use in your code. For example, you have the block of the DMA in the hardware. You may call this block from the multiple software unit. Okay, so each call is called as an instance of the DMA. So for that you need to use this structure. Okay, AXI driver instance. And then if you want to know all the information which you have configured in the hardware DMA, then you will use this structure. For example, what is the device ID, what is the base address, what is the, whether it has the MM2S port, whether it has the, what is the data width, everything is there. And from where it is copied from your xparameter.h file. So this structure, we need to fill it up from the data which is present in this in the xparameter.h file. So we need to have these two structures in our code, and then we need to make use of these functions. You can see all these functions to enable or make use of the DMA. Okay, so the first step we need to do is that we need to go to our main code. We are done with the software function. Now we'll come back to the hardware, and we need to now define the corresponding corresponding variables as well as the function for the DMA. So first thing we will start with we need to define the corresponding structures. One is we need to define it for the xDMA config, and this should be of the type pointer as per the requirement. So we can say that the DMA config pointer. Okay, this is the one structure we need to define. Okay, and the second is the DMA instance. So this is the structure we need to define, then the DMA instance, then this should be our AXI DMA instance. Okay, so these are the things we need to define. Now we need to copy all the data which is there in the x_parameter.h file into this config pointer, and for that we have this function. Again, this process will remain same for all the IP you will use in the feature. So you can see that for this one, you can see either you can copy it by giving the device ID or by giving the base address by any information. So we'll start with we'll use the device ID. So I'll use this function. Okay, x lookup config. Output will be the all the pointer where all the data will be stored. And what should be the input? Input is the device ID, and the device ID, you can see that you will take it from this here. Okay, so I'll just pass the device ID here, and that's it. Okay, so I passed the device ID. I got the all the configuration information which from the .h file. So I don't need to look at the .h file every time. I can use this pointer. Okay, then I need to create one instance of the DMA which I am going to use in this code. Okay, I can use this DMA, hardware DMA, from the multiple. I can have the multiple C code. I can use it. So for the instance I'm using in this one, I will initialize that one. Okay, so what I need to do? I need to do the config initialize of the DMA instance and with the corresponding configuration data. So here you can see that I'm going to do the config initialize. Okay, what is the input to the config initialize? You can see that the instance pointer and the configuration pointer. So instance pointer is, we have defined it as a structure, not structure pointer. So we will pass its address. And for the configuration, we have defined it as a pointer, so we can pass it as it is. And the output will be the, let's see what is the output. Output is a int. And if you go to this function here, you can see that what we are going to get is it will do all the initialization and it will return whether the initialization is successful or not. Okay, so what we will get is the status. Okay, so we can define this variable, status variable, as a int status. Okay, so we can define it anywhere, int status. Okay, so this we define it. We got it as a status here. No issue as of now. Now you can also check the status. Now we'll go to this function and let's see what this function is doing. So you can see this is the initialization, config initialize. So what is this? This initialize the DMA engine. This function must be called prior to using the DMA engine. So everything is given. Initializing the engine includes setting up the register base address, setting up the instance data, and ensure that the hardware is in proper state. Okay, so you can see that this is a very complex function, but at the end it is nothing but the reading and writing from the particular registers in the DMA. Okay, that is what it does. Whenever you have time, you can go through this function if you want to understand more about it. But it is always a good idea to go through this function line by line. Okay, so we have initialized the function. Now we can check whether the function is initialized or not. We can print, we can check the status. If the status is equal to 1, that means there is a successful, or if the status is 0, if there is some failure is there, or vice versa. So we need to see. So let's go to the this one and we will see what it is returning. If it is success, it is returning 0. Okay, so this success is a parameter which is defined. So that means if it is returning 0, that means it is success. So we can check with this one itself. What we can do is that, where is this function? Yeah. If status is not equal to this one, that means DMA initialization has been failed. Okay, so we can say that the printf DMA initialization failed. Okay, so that is what we can do. And if it is happened, then we can return there is a similar to the success, there is a return failure is there, so we can return failure. Okay, so this is how we can check by debugging. We know that if this statement is printed, then there is a problem with the DMA. For example, if you have not used the DMA and if you try to run this code, it will give us failure. So this is done. Then now we have initialization. DMA has been initialized. Okay, DMA instance has been initialized. Then what we are going to do, we are going to now start our timer. Okay, so let's do this one. Okay, so DMA is successful. So we are going to start the timer. So capture the timer value at the beginning. So we are capturing the PS. Now here it should be the PL value. Once we get the PL value, now we need to tell the DMA that we are going to, you should take this data, send it to the FFT, and you should take this much amount of data from the FFT and store in this variable. So we need to configure the DMA to perform this task. Now you can see that in our block diagram, the DMA is connected to the FFT. So DMA is sending the data to the FFT, and the FFT will receive the data. First, FFT will provide the output to the DMA. Now, in this case, we need to tell the DMA that be ready to take the output of the FFT and be ready to send the data to the FFT. So which one should we do first? Whether to send the data first to the FFT and then tell the DMA to be ready for the taking the data from the FFT. In this case, the problem is that the FFT is so fast that while the DMA is sending the first bunch of data, FFT might have calculated the output and it will start sending the data to the DMA. If the DMA is not ready to accept the data, or we have not informed the DMA to accept the data, then the DMA will not accept the data from the FFT, and then FFT will put the back pressure on the DMA input, and the FFT will not accept the data from the DMA input. So to avoid this back pressure, what we do, first tell the DMA that be ready to accept the data from the FFT and then send the data to the FFT from the DMA. And how to do that? Again, there is a function. You can see that there is a simple transfer function. We are not using the scatter gather. We simple transfer DMA pointer, which from where the data to be written or from where the data to be taken, how much data, and the direction, whether from DMA to FFT or from the FFT to DMA. So let's take this function, X simple transfer. Okay. So in the simple transfer, first is the we have our DMA pointer. Okay. Second thing is let's go to this one. What is the second thing? Is this pointer of buffer address. So first we are telling the DMA to receive the data from the FFT and store in the FFT output. So what is this FFT output? We have the FFT output PL. Okay, so FFT output PL. Then we are telling the DMA to take this much amount of data. What is the amount of data? One is the FFT size. Okay, that is the total amount of data, that is the FFT size. But each these are in FFT size is 8, that means 8 elements. But what is the size of each element? So it will be size of, okay, it is the float complex. Okay, so this is what it says, that it is a size of float complex into the size of float complex that is done, and into the FFT size. So this is the data amount of data we are going to send. Okay, So, and the last one is from where to where. Okay, so XDMA, where is this function? Simple transfer, right? A direction. So the direction is either from device to DMA or DMA to device. So first is that we are telling the DMA to be ready to receive this much amount of data from the device. So we can say that from device to DMA. So this is what our first one. And here we will get the status. What is this status? This status says that DMA has been configured. Inform the DMA to receive the data from FFT. Okay, the transfer has not been started. This is just we are telling the DMA to receive this much amount, to be ready to receive this much amount of data. Now, similarly, we are doing the another transfer. Now, this time from the DMA to FFT. Okay, so let's go here. From simple transfer, same AXI DMA. Now it should be from the FFT input, right? So this is the FFT input. FFT input size is same, but now it should be now in the opposite direction. It should be from DMA to device. We are telling the DMA now start sending the device data from the to the device. Inform the DMA to send the data to the FFT. Now this status indicate whether the information has been sent correctly. DMA has not may not be have started the transfer. Okay, this is just to tell the DMA that information has been sent correctly or not. Now this has been done. Now you can see that we have done the simple transfer. Now what we need to do? Now in the background, DMA will start sending the data. With DMA will start looking for the data from the FFT. So the process will keep on heading. Now we know that our data has received from the DMA only when the DMA has been in the ideal state. Then only we'll know that the data has been received from the DMA. So we need to check the ideal state of the DMA. Okay, so now I need to know whether the DMA has completed the operation. Again, I can use one of the driver function which is there here, but now I'll explain you how I can write my own driver function. And for that, I need to understand how the driver function need to be written and what should be, how the registers are mapped inside the DMA. Okay, so to understand that, let's go to the DMA document. Okay, so if we want to understand the how to check the status of the DMA, we need to go to the corresponding document of the DMA again. Okay, so in the corresponding document of the DMA, you know that there are registers are there, and we need to know the status. So you can see that there is a status register for the memory map to stream, and there is a status register for stream to memory map. And for this content of the register, you will see that there is a first bit which is the LSB second LSB bit, which indicates whether the DMA is ideal or not. So we need to check the status of this bit. So let's go to our SDK. Okay, so in the SDK, so me write the function which is the status, which is the check DMA ideal, and to the DMA what I should send. I need to send the base address of the DMA. Okay, so I can send the base address of the DMA. So where is the base address? I think I have used for the initialization. Okay, so this is the device ID is there. So I can go here and I can copy the base address. Okay, I can copy the base address here, and I can copy the offset. So first offset is 0x4, and then I'll see the status. Now again, this function we need to write it. Okay, we will write it, and I'll need to make sure that this status, I'll keep on calling this function. So while status is not equal to some value, which is that value? It should be equal to 0x00 32-bit value 002, because you can see that I want to check the second LSB bit, so that's why 2. If that bit is not set, that means DMA is not ideal. So I'll keep on calling this function. Okay, so this is how we'll keep on calling this function. You can write the parameter for this one, that is also possible. So let's write the parameter for this one. So as define that is the DMA ideal mask. Okay, so this is the DMA ideal mask. So let's define it here, and we can make use of it here. Okay, so the code becomes more readable. Now we can write it as again, we can create a mask for this one as well. Okay, so let's write another mask as defined DMA mm to s register offset. Okay, that is 0x4. Okay, so this is memory map to stream, right? This should be memory map to stream, if I'm not correct. Yeah, this is memory map to stream. So then I have to write another, which is the register offset for stream to memory map. This is for 34. So I can write 04 and 34. So memory map to stream. Where is this code? Okay, yeah, memory map register offset, and I'll just check it. Now here, after I'll come back from this loop, I know that the transfer has been done. Then I'll check it in the another direction. So again, same, only that the offset will change, the register will change. It will be S to memory mapped, and the same offset I'll use it here, S to memory map. So this is done. Ideal mask will remain the same for 1 because that ideal bit is semi-common in both the one. So now once I am done, that means I know that the transfer is complete. So then I'll do the corresponding stop time. I'll get the time so that I know how much time it took for the execution at the PL. So it should be PL stop. Okay, it should be PL end. So that I'll use it here. So it should be get PL end. So at the stop. So with this, I have completed the FFT operation of the hardware. Now I need to see, I can't just print the output of the FFT software and hardware. I can't print it, right? I need to compare the output, and I need to make sure that the output is correct or not. Okay, so let's modify this function, compare PS and PL output. Okay, so we need to modify this function. Okay, basically what we are going to do, we are going to compare line by line, and then we are going to check whether the output is correct or not. Okay, so in this one, okay, so here we have written this function. where I'm comparing the line by line every output between the PS and PL. I'm also printing the output, and then I'm saying that if the difference between the both output is greater than certain value, then I'm generating the error flag. So based upon the error flag, we can display. So if error flag is equal to 1, okay, that means printf, there is a error in the, or we can say that the data mismatch found at, we can give the location %d. Okay, so we can give the location %d. We can display the corresponding data also, but we don't need to, because we have already printed the data in the beginning, so we don't need to display the data. So that is the index is j, is the time at which we came out. Else printf functionality is verified successfully. Okay, so this is how we have compared the data and then we have verified the functionality. Now the next is the execution time. Execution time will remain, the process will remain the same. So we'll do the same thing for the FPGA. So we'll do this one. Okay, so let's, instead of the processor, we'll have the time PL. So here we'll have the PL and here we'll have the PL. Now this is complete. There looks like a couple of errors. So okay, we have not yet written this check ideal function. Now what we need to do in this check ideal function? Now in this check ideal function, we need to we need to read the data from the DMA register, like we need to write our own driver function. So this is int check ideal. Okay. So what is the input we are getting from the is the base address and this one. So that is of the type, let's look at the, yeah, U32. Okay, both are of the type U32. So where is our check? Yeah, U32 base address and U32 offset. Okay, these are the two values we are getting and we are returning the status. Now what we need to do, we need to read the register. So do we have any function to read the register? No. Let's see, because these are all the people are also reading the register, right? Reading or writing to the register. So let's see, go to the function. Are they using any read register? Not here. Not here. Okay, so not in the initialization. Okay, let's see, reset one. Are they reading any register? Not here. So we need to keep, oh yeah, you can see this guy is writing to the register. We want whether there is an option to read from the register. So yeah, so you can see that we by using this read register function, which is there, we can provide the base address and offset and we can get the value. So our job is done. So we can use the read register. We can use that in 32 as well, where we need to add them and then pass it. So either of them we can use. So let's use the read register. Okay. we'll pass the same value, which is the base address, and we will pass it to the offset. Now from this we will get the complete register. Do we want a complete register? No, we want only the second LSB of that one. So what we can do, we can add the output of this one, which is the 32-bit register, with the corresponding our mask only, right? Which is so that it will retain only the second LSB. Okay, so that is what we'll do. We'll do the AND operation so that we'll get the corresponding status and then return status. So you can see this is how easy to write our own driver also. We have not defined that one, so we will define the integer. Okay, so this is fine. Let's look at the this one. It is returning the 32-bit integer. So it is for the safer one. You can integer is also 32-bit. That's not problem. But for the safer one, we'll define it as a uint32. Okay, unsigned 32. So just safer way to define. So the code is complete. Now we are done. Now we will verify whether the code is complete or whether the code is working or not. There will be one error. I'll leave it to you figure it out why this error is, but we'll see that in the next video.